Okay, so in this video, I quickly want to look at question 5.2, how to construct molecular orbitals. I will speak through essentially how you're going to construct molecular orbitals for butadiene and try and give you some guidance on how you can do it for the others, because the others are just an extension for what we do in the practical guide. But now you can see it stepwise how I went about it, and hopefully that can guide you to answering your own question. So let's consider the case of butadiene. So butadiene has 4 carbons, it contains 2 double bonds. And if you remember from your second year organic, um, double bonds contain pi bonds. And pi bonds, of course, are the second bond of a double bond. So if you look at ethene, for example, your sp2 orbitals bond in a sigma fashion, and then your p orbitals can overlap sideways to form pi bonds. And those, in other words, in each of these carbons, there's going to be a p orbital sitting on this carbon, or on each of these carbons that can overlap to form this pi bond, the pi bonds that you see here. And these are what we're going to mix to get the pi molecular orbitals. Okay, so that is what we essentially want to look at. Which, if we use the p orbitals to make pi bonds, there are 4 p orbitals in butadiene, right? And each of these have different 2 phases. So in other words, we have 4 different kinds of combinations. So, either all in phase, switch 1, 2 in phase, 2 out of phase, etc. And how you're going to do that is in terms of your possibilities. So the lowest energy orbitals will be the ones, well, firstly, so the lowest one will be pi molecular orbital. Pi, very important, pi molecular orbital. So not sigma orbitals. So remember, there are many sigma orbitals also in this molecule, but we're focusing on the pi molecular orbitals. And those form the frontier orbitals, so HOMO and LUMO orbitals, and the ones around them. So to form any of these, you're going to look at your pi orbitals. So remember, I said you combine them. So the first option is they're all just as drawn there. You have them in phase. That leads to an orbital that looks, or molecular orbital that looks something like that. Okay. You can also have 2 in phase on this side and 2 in phase on that side. So this one is all in phase. This is sort of 50% in phase. So half in phase, half in phase. That's why I say contain them most constructive overlap. Constructive overlap meaning they loop together and to form a molecular orbital. Because they're p orbitals, they are involved in the pi bonds. So these are called pi molecular orbitals. This is the lowest energy pi molecular orbital, not lowest molecular orbital of butadiene, the lowest pi molecular orbital energy, or lowest energy pi molecular orbital of butadiene. This one is the second lowest. Okay, so you're getting where this is going. So now let's say we switch one of these. That's the next idea. And we're getting to the least constructive overlap. So that is, now that there's going to be one kind of overlap, 2 that aren't overlapping. So third least amount of constructive overlap gives you something that looks like this. So you see these 2 are overlapping, these ones are on their own. That's why it's the second highest energy pi star molecular orbital. So this means it's an antibonding pi molecular orbital. And then finally, if all of them are out of phase, so in other words, if you look at the sine curve, that is what describes it, you can see all of them are out of phase, and that is how your molecular orbital looks. Okay. So if you look at that in terms of the molecular orbital diagram, if we think just about the pi molecular orbitals. Remember I said there are sigma, so if you're going to calculate this on beta mol calc, I do advise go calculate for butadiene. Go and look at it and see which of these orbitals are the ones I'm looking at. And you'll see that it is the last two minus and the first two plus. When you remember, if you look there on the left-hand side in terms of the orbitals. That's what I say, they are the frontier orbitals. So that is why we're looking at pi orbitals and not worrying about the sigma orbitals, because they're easy to identify and they come from p orbitals. Okay. So the molecular orbital diagram I drew for you there is an abbreviated molecular orbital diagram, and that is only for the pi molecular orbitals. So in other words, there are sigma things happening all around it, but this is just for the pi molecular orbitals. In other words, this pp overlap. So there's no sp or anything else like that. It's purely p overlap. And p sideways overlap, which we're looking at. That's why it's called abbreviated. So it's not the complete one, just a small snapshot of it. And if we look at this part, so in other words, the highest pi bonding molecular orbital and the lowest energy anti-bonding molecular orbital, and you go and fill your electrons that you have there, right? So there are two double bonds, so that means 4 electrons in pi molecular orbitals. So that is why you fill the first one, the second one, and then you call them HOMO and LUMO. So that gives us your HOMO-LUMO orbitals. Now you see how they look. So this little block gives you what is called the band gap of a material, and that is just the energy difference between the HOMO and the LUMO orbitals. So this value minus that value, or that value minus that value. Doesn't matter how around you do it, you're going to get a positive value. And then that gives you, so that's the amount of energy that you need to excite an electron from your HOMO to your LUMO. And it should be quite intuitive. Maybe it's not, maybe you should never use the word band gap before, but that is what it's called. And of course, this dictates a lot of its absorption properties. In other words, what its color is, like you did for complexes in 385. Also UV-vis absorption, you can get from that. So in other words, that energy tells you what does the energy of the photon, or the incoming photon must be to excite. Plainly what it is. So remember here, we started with 4 p orbitals. So now if we add an extra p, another double bond, so in other words, we start with 6 p orbitals. How many pi molecular orbitals do you expect? Okay, very easy, right? You can also just calculate it and look at it. And then also consider it in terms of, if we put it in a ring system, does that change things? Just think about that. So you're going to look at these two specifically, but first go through it for butadiene. Make sure that you are able to assign them. This one is a straightforward extension of this one. And the benzene might be a bit difficult, but I want to see what you try, what you get, what you come up with. Because try and hybridize. Remember, hybridization, this idea that we have here of bonding with the p orbitals, is a specific model, and then we're looking at computational. Butadiene aligns perfectly with what we've predicted. Maybe benzene doesn't, maybe triene doesn't. It all depends, so that's what you need to describe. You need to look at it, so there might be differences, there might not be differences. That's actually what I'm trying to say. So don't worry if you don't see what you've predicted here and what comes here is not the same, but just explain it. Why do you see differences? Why might there be differences? You also need to, in this question, derive the molecular orbitals using the p argument, and then you calculate them, so then you're going to see, and you also look at the HOMO-LUMO gap, and you're going to compare that to some literature values, etc. And you can see how well the theory matches this situation. And if any of you are interested in doing a 2D particle in a plane to calculate what the energy gap is from quantum mechanics, you can also do that, but it's not a requirement. Okay, I hope this guides you a little bit more. Just go through the video, draw it step by step. As I showed you, and I promise it will start making sense. Now you haven't done this before, but just spend some time on it. It's actually quite intuitive once you start. Okay.